We hope to have a panel after the next set of speakers. So we will jump right into the official first afternoon session after this keynote, and Kemp will kick it off. You heard from Kemp when he asked a question just before lunch. I met Kemp when he was a master's student here a few years back, and I'll turn it over to you.
Thank you, Martin, for the introduction. Yeah, I graduated from Stanford in 2018, so it has been 8 years, and this is the first time I come back and join this forum in person. So the topic today I would like to share with you is generative design using a keto parse approach for industrial construction. And I'm Jianpeng. I'm assistant professor from the Department of Real Estate Construction, the University of Hong Kong. So these are some of the projects I worked on before, and what I'm going to share with you today does not represent any of these funding agencies. It's just my personal opinions. So previously I like to work with industry partners, like during the master's. Like I worked with the design firms, and during the PhD, I worked with the manufacturers and the developers. So I see like different perspective like from them, like on the industrial construction. So across the world, we see like all the economic bodies are trying to figure out the most effective and sustainable approach for the construction industry. In the United States, there is like such investment raised for the initiative in industrial construction, focusing on the productization, demand aggregation, and capacity growth. And in Europe, this emphasizes more on the building renovations using the prefabricated construction approach. And in China, recently, like this like prefabricated construction is also regarded as the most sustainable and green construction approach. In Hong Kong, the public housing is currently the primary application domain for modular integrated construction. You might see that is the terminology used in Hong Kong for industrial construction. So I like to start my presentation with this slide because it always reminds me to keep track of the latest policy and news on industrial construction. So if you have any latest news, and please share with me, I would appreciate it. So when we talk about industrial construction, I see we also heard about other terminologies like the precast construction, modular construction, modern methods of construction. Yeah. So and all of them like share some commonalities and also have some differences. So if you see from the project delivery process, they are all like manufactured or produced in the factory, transported to site, and finished assembly on site. And from the design, because this presentation, this talk today, I will focus on the design stage. So during the design stage, you need to consider like all above process and how, as well as the constraint, how to integrate them into the design process. And from the product point of view, for example, the precast construction involves the products from like ranging from the precast facade, panels, slabs, beam, and columns. And on the other hand, the modular construction is a more like integrated approach that includes the structure, like the building systems, and the finishes all together. Okay, so this product has variations. For example, from architecture functional perspective, we can classify them as the single-room modules, like the kitchen and the bathroom parts, and we can have the multi-room modules that's usually serve for the apartment. From structure perspective, we have the closed module, where you have like the complete enclosure from 4 sides, or you have the open module, which can be used to form a larger space. Of course, materials also varies. Like in Europe and the United States, we see like the timber are more popular, but in mainland China and Hong Kong, like the concrete is more like widely adopted, and as well as the steel modules, and particularly steel is efficient for the transitional housing because it's easy for disassembly. Okay, so then let's move to the generative design. Why do we need generative design, and what benefits can it bring to us? So I have heard answers like previously. For example, people talk about generative design can provide you with like a rapid generation of design solutions. And people also talk about the generative design can predict the building performance or construction performance. And of course, in the end, the generative design can provide you with decision support systems like built on this multi-object. If you have multi-objectives, they will use this optimization algorithms to help you figure out what is the optimal solutions for that. So these three most cited benefits are also reflected in this 3 steps typical generative design workflow: design generation, performance evaluation, and optimal solution search. So before I move on, I want to do a quick show of hands. How many of you believe or think the first benefits, like the rapid generation of design solutions, adds most value to your project? Okay, and how about the second perspective, predictive evaluation of building performance or the construction performance? Okay, and the final one, the optimization, help you either reduce cost or reduce the time, or if you face multiple objectives, help you to figure out which solution is the best. Okay, perfect. Yeah. Actually, this question is not that scientifically rigorous because all those 3 steps are interconnected and or interdependent in this generative design process. Okay. Actually, the generative design is not a new method. It has been evolving many decades. It first emerged in 1960s with the development of computer-aided design. More recently, the fast, rapid advancement of AI has given this concept new momentums. This is why you see a lot of AI-based layer generation use generative models, and with the introduction of large language models, users are provided with a more easy interface to customize their design using the prompt. And you also see this user-guided generative models that helps you step by step to refine your design, also from the 2D to 3D models. Okay. So, however, existing generative design approach mainly focus on the design itself, while seldom or pays much less attention to how the design is constructed. For example, what construction method do you use? Do you use the cast in place, modular construction, or 3D printing, robotic fabrication? And what are the manufacturing constraints or capabilities? And how do you involve or how do you incorporate those constraints and feedback into your design process? This is what I want to draw your attention to another value-adding point of generative design, that is the coordination. So here, the coordination does not only refer to the design coordination between the architects, structural engineers, and MEP specialists, but also the project coordination among the planning, procurement, production, and operations. This is also my research vision to see generative design not only as an approach to create the form, to create geometry, but also as a coordination framework to link design decisions with project construction and delivery. Then let's talk about some technical and theoretical foundations for my research, and this is also helpful for you to understand how the generative design system works. So the first component is called modularization. It is design methodologies to help you decompose a building into a set of standardized or semi-standardized module units, or more broadly speaking, the kito parts. So there are 2 typical strategies, top-down and bottom-up. If I have to summarize the difference between those 2 approaches in one sentence, I would say the top-down modularization bricks are predefined. So you see on the left-hand side, bricks are predefined the reference design into the modules or panels. This approach gave you much design flexibility, but limited standardization. This is why you see the modules in different sizes and panels in different geometries. And on the other hand, the bottom-up approach assembles already standard or semi-standard modules or units into design, which has higher standardization or industrialization, but reduce the customization capabilities. Okay, and from the project delivery approach, the top-down approach is more suitable for or commonly adopted in the traditional project delivery process, where the module manufacturers are involved in the downstream of the process. If you are familiar with the customer-driven production strategies, these are more used for the engineering to order products. And for the bottom-up approach, that is more like widely adopted for the projects that for the developers that adopt the like integrated project delivery, where like the modular manufacturers are involved in the early design phase, and that is used for the assemble-to-order products. This is a second component, graph modeling. It's a little bit mathematics. I quickly go through it. So the graph model is like so graph is like a data modeling approach, like to represent the complex data. And here is an example how graph model can be used to represent apartment, where you can see the room can be a node, the building elements such as a wall can be a node, and the edge can represent the adjacency relationship or the structure or hierarchical relationship between the room and the elements. The reason why I emphasize I put the wall as a node here because the wall plays a crucial role to determine the modularization strategies. What do I mean by that? So here is an example. If you look at the figure, so here I will show you how different modularization strategies can be represented using graph modeling. So if you look at the figure A, that is the wall graph. So each node represents the wall instance to represent the above, like the simple floor plan. And starting from the figure B and C and D, you will see I cluster the set of nodes together using different color. Each cluster represents a module. So for figure B, basically we represent like 4 room units as 4 individual modules. And for figure C, we combine we combine the kitchen and the living room into 3D modules. And for figure D, we combine another 2 rooms, but the shape is a little bit irregular. And finally, we do not use any modules. For the last scenario, we just use the fully parallelized approach, where we combine the wall instance into longer manufacturable panels. Okay, so this is how different modularization strategies can be represented using graph models. So far, we have introduced you to the kit parts, different product variations. We introduced you to the generative design and graph-based modularization. Let's move on to show you some like practical applications or prototypes. So the first application is a kit part library, and this is developed with a collaboration with Imperia, a Swiss developer, and the Zurich University of Applied Science. And this project is funded by the Swiss Innovation Agency. Okay, so traditionally the product information is stored like in the separate data silos. Most of the time you see the spreadsheets like are used to store the product data. So or the sometimes you will also see the CAD drawings or the 3D models, the BIM models. So the kit part library basically provides you a data-centric and graphical interface for you to browse like different type of products, visualize them in 3D views, and examine the key attributes of the products. And finally, you can export them in the standard data format, such as IFC, for the further analysis. And the second application is the 2D to BIM or PDF to BIM. The goal is to automatically convert the traditional 2D plans to the BIM models. Basically, it involves like 2 critical steps. First is the geometry development, and the second is semantic enrichment. So here you will see how we pass a floor plan as a PDF and annotate the room types, room boundary, and apartment partitions. And all this information, like the coordinates, the dimensions, are encoded as the standard JSON format, and then are used for the 3D geometry and development. And to enrich the semantics, basically what I mean is you analyze the floor plan and select the appropriate products from the kit part library, and to match them with the developed the 3D geometry. Okay, so this is done by the graph-based rules. So if you remember, we talk about the room layout graph, which stores not only the room properties but also the room-to-room relationships. And this graph-based representation can help you perform the inference and select a product which satisfies the specific room requirements, such as the fire protection, moisture resistance, or the noise insulation. Okay, so that helps you to determine like what is the appropriate products from the library. And this application is for the modular developers or designers. What we propose is a data-driven framework to help you identify what is the most representative module platform that match the local market demand. How we are going to do this is we collect a bunch of data sets that represents the local multifamily residential housing project. And we use the pattern mining algorithms, and basically we identify what is the most frequent what is most frequent like module patterns and among the historical data sets, and we define the number of reoccurrence of this like module in the historical data as support. Then the user can basically input the module features such as like number of rooms to support multi-room modules, maximum module width to account for like the production or transportation constraint. They can also like input the module shape regularity, and this is basically for architects to exclude some irregular configurations of modules. And finally, you can input the support threshold to ensure the statistical significance. Also, make sure you match the local market demand. And besides, this tool can also be used to give you the room combination distribution analysis. In other words, this basically tells you what kind of room combinations are more like cost efficient for the 2-room modules, for the 3-room modules, or for the 4-room modules. Okay. And finally, if you want to develop a module, you have the idea, you have the room combination in mind. For example, I want to develop a module composed of the bathroom corridor and another bathroom, and what would be the possible layout of such modules? And all these like generated design solutions are coming from the historical data. So that represents the local market demand. And this application is an improvement on the existing prompt-to-design approach. So in the first row, you will see the existing how existing like prompt-to-design approach works. So you give a prompt, you can also give the size boundary, and then the algorithm will generate like multiple floor plan variations. And one thing need to be noted that at the very beginning, these algorithms can only deal with the regular size boundary, and now we can upgrade it to make the irregular site boundaries works. But more importantly, it's the second row. You see, we can enforce the system to incorporate to use the specific modules. For example, the module prototype identified in the previous steps, or your patented product. You want to use it to develop your modules, or to develop your project. So here you just add one more prompt, and you will see like how these modules in the red and the yellow be used in the floor plan generations. And basically the algorithm will rearrange the floor plan and accommodate the module in the floor plan. Okay, so the last application I want to introduce you to is this like optimization engine, where this is like collaborated with Santa Clara universities. Basically, we embed the cost and construct time estimation into the optimization engine. Of course, you will see like different projects, different companies. They have their own measurement of the cost and the time. But this is like so basically this like you will see on the right-hand side, this Pareto front can be generated for case by case. But what is so I want to highlight is like if you look at the Pareto front, like from the left top corners to the right bottom corners, you will see this basically follows the fully parallelized approach to the fully modularized approach. So if you give me a design like this, algorithm can help you identify which space in the given floor plan should be first prioritized for the modular construction. And in the end, it will help you to identify, because we in the previous slides we see like given a floor plan, we have like different various modularization strategies. So this optimization engine will help you to locate which modularization strategy is like more cost efficient or gives you the shortest like construction durations. Okay, so as a summary, I will put all those 6 components in a framework. So at the data layer, we will collect the data set. If you have like 3D models, that's more straightforward. If you do not have that, you have 2D drawings, then we can use the 2D to BIM to enrich the semantics. And once you have a data set built, you can move to the Kito part layers. You can identify the most cost-efficient modules to represent the local market and to manage the data using by developing a Kito part KitObas library. And then once you have the KitObas library developed, you can select the modules and to develop your project. This is how we translate from the project to product approach. And once you have like various options of the design, the optimization engine will help you to choose the most construction efficient approach. Okay, so this is like the overall like framework of the generative design, but this generative design you can say different from the existing generative design approach. This is particularly efficient for the industrial construction. Okay, so that basically ends my presentation today. Thank you all and welcome to any of your questions.
Thanks, Kemp, for this primer and then deep dive in generative design to support industrialized construction. So we'll move on to the next speaker, Sol van Kempen from Sustainer. Sol is the CTO and co-founder of the company. Sol is joining us from the Netherlands.
Yeah, thank you for allowing me to do this virtually. From Amsterdam at midnight. I wish I could have been there live, but I'm very thankful that this way I can still be part of this event. So today I want to show what we do at Sustainer. So I'm going to share my screen and have a little presentation and then a live demo, which I think it's a bit more exciting. Usually doesn't go wrong, but you never know. I want to do a few things. So I want to talk a little bit about why we are doing what we do, why is Sustainer, how do we get here, and then I want to do this live demo. So basically, to start with, Sustainer develops a building system and software for modular wooden construction. So what we don't do is we don't build anything. So as Sustainer, we are basically, so I think the reference we use is this Intel Inside. We are the technology that helps you to build your wooden modular buildings, a bit like this. And now, why do we do that? We do that already for 10 years. And I want to kind of start a little bit with our origin story. So we're basically started about 10 years ago with a bunch of people who believed that they could change the world and make it a bit more sustainable, save the world from climate change. And that's what we started to do. And originally, the very first thing we made was actually very different from what we do today, which was a self-sustaining shipping container, where we put some windmills on the roof and some solar panels, and we had our own water filtering system. And we thought we can, basically it's a fully self-contained off-grid system. But nobody really wanted to buy this, so that didn't really help. And also, after like 2 or 3 years, the Dutch government moved to a new policy where basically it became normal or like required to build close to energy neutral. So basically, the energy used during your life cycle of the building should be close to zero, which basically left us with one new challenge, which is how to make the building itself sustainable and not just during use. So what we want to do at Sustainer is create an unfair advantage for bio-based construction. So what I mean by that is, well, first of all, why do we need bio-based construction? That's because 8% of all CO2 emissions in the world are the result of cement production. Right, so 8% is the same as the US, more or less. So it's if cement production would be a country, it would be the second biggest emitter of CO2 in the world. This is what we set out to solve, and we think there's an opportunity in this graph. So what you see here is basically the growth of the total economy, manufacturing. So basically, this is kind of the efficiency of different sectors. So basically, you can see that manufacturing is more productive than 25 years ago, and even more productive than the total economy, while construction basically gets less productive every year. We need more people to create the same amount of square meters, or at least doesn't really grow. And we saw this as an opportunity to basically use to make bio-based construction more affordable and therefore more of an interesting choice for consumers. So basically, this is what we want to achieve. So the concrete keeps increasing in price, or it stays sort of the same over time. Whereas what the goal is of Sustainer is to become cheaper than traditional building methods. Currently, we are at about price parity, and yeah, we're working very hard to make sure that we eventually become more affordable and that it becomes the obvious choice to choose the bio-based sustainable solution. Now, we do that in 4 different ways. So we use off-site construction, minimal material use, mass customization, and vertical integration. Now, off-site construction looks like this. We have 2 factories running, or 2 factories we work with. We don't own the factories. And the factories produce about 150 to 200 houses per year. We assemble those buildings in about 15 minutes per module. It's a 3D modular system, and therefore you can build about 8 houses in an apartment building per day, and then a whole building like this in a few days. Of course, it depends a bit on the other elements like foundation, etc., which have to be on site before. Now, this is kind of an exploded view of what we make. So we have a 3D modular system with very, very high quality elements, which have an extremely high precision rate. And that's the ones that we place on top of each other. So this is kind of like how we build it. Usually these days we build it fully, including installations and facades. So that the work on site per house can be done in a week after placement. The second important thing that we do is we minimize material use. So as Sustainer, we work with a CNC milled wooden system, which means that you have higher costs in your elements, but you solve that by having fewer cubic meters of wood, basically. And in this way, we can minimize the weight of the elements, but we can also minimize costs by being very, very efficient. Well, that looks a little bit like this in reality. So I have a little video here. You see some people assemble. I think in a previous presentation, people also said we have no automation. Well, at Sustainer, that's the same. Basically, the automation is in the elements, and there's very little automation in the factory because the assembly time is very low. Most elements connect in wood-on-wood connections, and they need very, very little labor to produce. So you can produce a house in about 150 hours, which is much lower than the baseline is in the Netherlands. We go quite far. We CNC mill all of the holes for fasteners in it, and we even mill the entire floor plan onto the elements so that it can be built by people with very little experience. So usually people are up and running in construction in about a month. That's how much training they need to be able to start making a house. So I'm not going to show this entire video because it's a little bit long. Let's go to the next one. Yeah. Then mass customization. So at Sustainer, we make modules in every size. And the reason for that is basically that this is how we look at projects. So you've got projects which are large scale and very, very simple. And they are the most interesting, of course, for prefabrication. And that's where most of the prefab currently happens. Then there's like the main bulk of all houses, which is a little bit more unique, but not very special. And then there's like the very special buildings, which are like museums and theaters. And they are just almost impossible to do in a very, to do prefab. So almost all modular builders kind of focus on this first area, on these projects that are the easiest to prefab, and we don't do that. We focus on this sort of middle part, on all the buildings that you cannot do if you only have 1 or 2 or 3 standardized modules, but that you can only do if your module is fully flexible. So we built that system over the course of 10 years. So we started with a lot of private houses, like about, I think, 200-300. And then eventually we moved to sort of larger scale production. And now these are the projects that we're doing. They're mostly apartment blocks with a few hundred houses each. But what is interesting about these projects is that almost all of the apartments in these blocks are unique. None of them are a copy of each other. And one project can use about 50 to 100 different module sizes. And there's no copy of a module in it. So now, how do we, so the last pillar there is vertical integration. Basically, most software is kind of is a horizontal software, right? So you've got like your briefing, and you've got like software for sketch design, for technical design, for your construction, for your ERP, etc. And what we think we can improve is by doing that fully vertically. So we make one little plugin that basically allows you to do the entire process in one go. And the advantage of that is the following: like usually your information during your project design goes up, but you lose a little bit of information at every transfer, right? So this is basically the promise of BIM, right? Like the moment you say, we just have one place where we gather all the information, then you can basically just add the information in the beginning and use that during all the other phases. Now I'm going to show that live, which usually works, but I'm always a little bit nervous about it. So this is kind of a plugin we built on top of Rhino, which is an existing drawing software, and we built a plugin there which uses that kind of basis to work on. Usually what we get is a Revit drawing that we load into our software, but this time I'm going to show you from scratch because that's, it's just visually a little bit more interesting. Here you can see some modules that we play. So I'm just going to put a few modules there, but I'm also going to show you that I can make a fully new size that I've never made before and place it next to it. And I'm going to make this into a building which is about 2 stories. In total, we currently do up to 10 stories in wood. Otherwise, it becomes a bit more complicated. And what you see now is that I just placed a few blocks here, but in the background, it's building a kind of abstract model of what those blocks mean. So here you can see the relationships between those blocks. So you can see this is a very lonely module, and these modules, they are connected and have some relation to each other. So this module knows it's connected to that one, and it has a certain facade type of relation here, but there's also a purple line which describes a connected relation and a orange line which describes a separated relation, like it's a separation wall between 2 houses. So basically that's what happens in the background, and because of that, what we can do is we can basically download a lot of elements that we've pre-generated from a database. Now, not all elements are in the database yet, because some modules have never been made before. So in this case, this module has never been made before. So what happens now is that we send a request to the server, which will slowly generate this module, hopefully during this demo. So we can add more and more detail to this building. So I'm gonna just make a few windows. I don't know, they can, so we basically allow for a lot of freedom. So you can make your walls every thickness you want. You can make your windows whatever size you want. You can put them anywhere you want. And it all has to work within the software. And what happens in the background basically now is, so this will also be requested, right? So these will now be requested at the server. But at the same time, we actually already have a model which is fully detailed. So if I look at this module over here, then you can see that this module has a lot of information. It knows here it was kind of connected, but also it knows that this is a roof, and it has all of the details up till the airtightness, the foils, etc. Everything that we need to produce this module, and that goes pretty far. So if I actually go into one of those elements, you can see a little bit of the complexity there. So this is a beam, and this beam is, as you can see, a little bit more complicated than an average beam. It has a lot of detail in there, which allows us to make certain types of connections that increase inherent stability in the module and therefore allow us to use less material. But also behind this beam, there's a whole model which actually provides the CNC milling instruction. And you can see that the beam, it's very hard to see, but it's slightly curved at the bottom to make sure that it's perfectly straight. Well, we calculate that on the fly. As you can see now, we've created this new roof that has never been created before, but it has the same sort of level of detail in there with all of these elements that I just shown as part of it. Now, these elements, they're so what you can see is that like this 3D model that we now have with all of these elements that can be ordered from the factory are basically a full description of the production that's necessary. So in this case, there's about 2,500 elements in this module. Most of them are fasteners, and they're all labeled and described. And what can happen now is that it can be sent to the factory, which can produce directly from this module. So of course, there's a few more steps, right? We also make some interior walls. We create installations, which takes a little bit more effort than the kind of just the basic setup. But within a few hours, we design an entirely new apartment, which we then have like to such a level of detail that we can send them to the factory and they load it into their system and basically order from that directly. And what we've been experimenting with recently, which I don't think we have shown that often before, but I'm gonna try to show that. Oh, there's this thing in the way, so I'm gonna. Is that we now try to so we've been doing this for like the last few years in this way, and we've kind of gone through the whole process to make this work smoothly. And what we're now as a next step experimenting with is how we can make sure that there's no more drawings used at all during the production process, where they run through this viewer, where basically step by step you see the information that appears. So you've got your beautiful building package, which has arrived from your suppliers based on the information in this model. And when it arrives, then in our model is also the information on when to build every step. So like what step to do first, what to do next, and then how to set it up. And what we're now experimenting with is like if we can have this as the only source of information in your factory, next to the fact that you've got this beautiful stack of elements sorted correctly to make the entire building without ever having seen a drawing, basically, which will allow us to work with fully untrained personnel. So this is basically what we do. With that, we make a large variety of buildings. It's all kind of in progress, and because of the presentations from before, I've also added a little slide to this presentation where I talk about the things that didn't really go well, but I wasn't sure if that's because I wasn't actually planning to tell it. But of course, there have been a lot of struggles to get here. We've done this fully independently with a team of about 25 people. And now we are at this stage where we're building a lot, but it's still like very hard to do that independently because a lot of companies want to kind of be in control of the whole process, right? If you're a big construction or company or a big developer, so that's one of the struggles we deal with. But it's also, of course, been very advantageous in some ways because you can actually learn from each other, which is kind of what we're trying to push always. And of course, finding capital has always been a challenge. So we've done it on ourselves, bootstrapped. Over all these years, but that's that has been interesting all the time, and that's basically my presentation. Thank you very much.
Thank you, Sol. I think that was the understatement of the day. It has been interesting to bootstrap for 10 years. So I bet it was. No, thank you. Very impressive. I always thought something like this, what you built, should be possible. And, well, yeah, here you are and showed it. Next, we welcome Takafumi Kozuma from Obayashi. Takafumi was planning to be here, but then he got sick and could not catch the flight from Tokyo. So sadly, he's also online, but probably better for him and for us. Welcome, Kozuma-san, to the ICF, and hopefully we get to meet in person on another occasion.
Yes. Okay, thank you very much. So, thank you for taking the time today. I'm Taka from Obayashi Corporation, and it's a pleasure to speak with you. And I was hoping to be here in person, but due to health reasons, I'm joining online today. So I'd like to thank the CIFE team for accommodating my last minute switch to virtual attendance. And I truly appreciate all of you for being here. I hope we'll have the chance to meet in person soon. With that, I'd like to begin. So today, I'd like to talk about 3 topics: circular timber construction, off-site manufacturing, and design for disassembly. Through the Wood Grand Ring at Expo held in Osaka 2025. This project actually using 27,000 cubic meter timber material that was representative of the concept unity in diversity. First, a quick overview of Obayashi. We are one of Japan's largest general contractor, founded in 1892, and now working with about 70,000 employees, delivering challenging projects in Japan and globally. In Japan, from the tallest tower, Tokyo Skytree, and to the newest baseball stadium, Esconfield, Hokkaido. In the Bay Area, retrofit work on the Golden Gate Bridge, and in Australia, a high-rise timber hybrid project. Under our philosophy, Make Beyond, we invest in next-generation construction technologies. And a little about myself. And by good fortune, I've gained experience across construction site, architectural design, using Revit, and cost management. This is actually an unusual career in my company. And today, my role is to bridge designers, engineers, and cost managers, so we can deliver large-scale timber projects that meet our clients' expectations. And I'm here because I want to help connect people who are passionate about sustainability and timber across regions and industries. But to be honest, I never expected that joining a construction company would lead me to planting trees, like you see in the picture on the left. So why did I end up planting trees? The reason is because we are promoting a vision called circular timber construction. Let me explain this diagram. Upstream, we contribute to forestry, developing new seedling cultivation techniques that combine artificial and natural light. Midstream, we strengthen the supply chain. Lumber processing and cross-laminate timber manufacturing companies is in our group. And the carpentry company is also in our group. So working together with them, we develop new solutions. And downstream, our core business, design and construction as a general contractor. But it doesn't end there. Beyond downstream, after building life ends, we reuse components as materials, interior finishes, furniture, and more. And ultimately, we utilize timber as energy. We even operate biomass power plants. And this is our vision, looking across the entire life of wood and making sure it circulates. Under this vision, we have pursued many forms of timber architecture: all timber, hybrid timber, wood finish building, and high-rise timber. Before the Grand Ring, I'll briefly introduce Port Plus on the far left. Port Plus is Japan's first 11-story all-timber high-rise. For us, it marked a milestone, mass timber moving from possibility to reality. At Port Plus, we developed the key connection detail, rigid cross-joint unit. It was not an off-the-shelf solution. Our design team engineered it for Japanese codes, constructability, and required performance. To scale timber construction, freeing these missing pieces through development is essential. And another key is offsite. We assembled a cross-shaped unit in a factory, shipped them to site, and erected the building quickly with less workers. This approach connects directly to what we achieve later on the Grand Ring. We also work with our Technology Research Institute to develop fire-resistant solutions. It is critical for timber in urban settings. To expand timber, we need not only structure, but also fire safety, acoustic problem, durability, and regulatory compliance. So these outcomes were not achieved by a single team. Architectural design, structural engineering, construction, and research and development worked as one. For timber, integration is a strategy. Wood grows from sunlight, needs low energy to process, and can serve many purposes. Yet it reaches its full potential only when we integrate the entire system. A quick question. Have you been to Kyoto? Do you recognize this place? Yes, Kiyomizu Temple. Traditional Japanese timber structure have long been supported by techniques called nuki joint. This is a key idea today. The Grand Ring is inspired by this traditional method, but engineered for modern scale and performance. And do you know what this is? It's hinoki. It's a Japanese cypress, valued for strength and natural durability, and widely used for temples and shrines. And interestingly, this is the surface of cross-laminate timber, CLT panels. This CLT was produced by our group company, Cypress Tsunadaya. They procure a huge amount of logs and process them with latest facilities. And actually, their high-quality CLT was used more than 70% of the Grand Ring roof. So now, let's move to the Wood Grand Ring. It was a symbol of the expo. The ring is 2 kilometers in circumference, and visitors can walk both above and below the roof. This is one of the world's largest timber structures. So collaborating with master architect Fujimoto, Obayashi was responsible for the northeast part, from detail design through construction. At this scale, existing method is not enough. We need engineering and production planning. And remember again Kiyomizu tempo and Nuki joint. A Nuki joint is a traditional Japanese timber joint in which a horizontal through beam is inserted into modest crown, typically without the use of nails and screws. For the ground ring, we modernize Nuki joint. We embed steel plate and drag screw bolts, then tighten the joint. So the crowns and beams are clamped together and ensuring structural performance. In other words, we translate inspiration into engineering. The assembly procedure is simple and clear. Set the hardware, insert, and tighten. That simplicity itself helps us achieve both speed and stable quality. And the ease of assembly also supports design for disassembly. If something can be assembled with a controlled and standardized process, it can be disassembled the same way. That becomes a technical foundation for reuse after the expo. Using this joint concept, we achieve a fully timber structure, crowns, beams, and roof, and reaching up to 22 meters in height. For example, crowns use 420 millimeter glue laminate timber, and the floors use 90 millimeter CLT. Selecting species and sizes appropriately for each row. So now let me show you how the ground ring was constructed. Yes. So most timber components are processed precisely in factory and delivered to site. First, we assemble planar units at ground level. We insert beams through the crowns. This is where the Nuki concept appears in the workflow. We stand the planar units up to form the lower structure. Repetition is the key to boosting productivity. The team improves the speeds cycle by cycle and connecting to existing ring to lock the frame. And next is upper structure. With safety first, we assemble as much as possible on the ground. Again, we start with planar units. Even when geometry is large, the principle is the same. Keep operation repeatable. And pass the beams to form a stable 3D frame, and then lift it. To guide multiple crowns accurately in one operation, we developed a guiding jig. Small innovation like this protect both precision and safety. And lifting 6 crowns and 12 beams in a single hoist, we place the 3D unit onto the lower unit. Then install CRT panels. Each panel is 2.4 meters by 8 meters, about 20 square meters per piece. We press them onto the ring frame and driving a long screw into the beam. By this process, precision plus unitization plus repetition, the ground ring takes shape. So let me summarize the benefit of this offsite approach using 5S. Safety, silent, speedy, sustainable, and smart. And this is also an answer to real constraints, the shortage of skilled workers, harsh site environments, and resource depletion. And importantly, ease of assembly supports ease of disassembly and reuse. To conclude, the ground ring is a real example of off-site manufactures and design for disassembly. And it is a concrete step towards circular timber construction. Yes, timber has great potential, and yes, there are many challenges. So that's why that is exactly why we want to collaborate with you. So timber is future. Thank you very much.
Thank you, Taka. As a guy who did his diploma in civil engineering and timber construction in Switzerland, so that was a nice reminder back to the roots. Thank you, presenters. As you can see from the schedule, we have reached actually the break time. So I think we need to take the questions. I have lots of questions, but I think we need to take the questions into the break and talk to the speakers here. And we will, I know it's very early in the day for you, Taka, and it's very late for you, Sol. So thank you. It's quite amazing to have a session here in California with somebody in Europe and somebody in Japan at the same time. So, but I was, really, I loved seeing the range of projects that we just saw in these presentations, and also how attention to process-related issues enable amazing projects like you showed, Sol. Buildings with very unique apartments that I'm guessing provide affordable customization or something like that. And then the scale of the ring, I guess it upstages the ring we have here in Silicon Valley. It's even longer than that. And then the projects, the scale of projects that Rosanna showed, also I find very amazing. And then the attention to tools and attention to processes that really make this possible came also through all the presentations. Kemp and Sol in particular, but also the other two. So thank you for enriching our discourse on industrialized construction with your experiences from different parts of the world in very different settings. With that, I think we should thank the speakers and take the questions to the break or then online. I already gotten a bunch of questions that people wanted to ask you, Taka and Sol, but we should try to stay somewhat on schedule. So thanks a lot.